Good evening, and welcome back. Tonight, we're setting sail into the smallest seas imaginable, not across oceans of water, but across the invisible oceans of reality itself. Before quantum mechanics, before probability and uncertainty, before particles learned to masquerade as waves, the world seemed simple. The apple fell, the planets turned, the machine of the universe ticked like a clock. But tonight, we'll peer beneath that clockwork, into the hidden patterns, into the shimmer of a world stranger than dreams. Before the word quantum meant anything at all, before scientists began to speak of probabilities, wave functions and superpositions, the world seemed clear, solid, and predictable. For centuries, humanity believed it had uncovered the very laws that governed reality, and those laws seemed both simple and eternal. Imagine standing beneath an apple tree in the late 1600s. An apple falls, tumbling through the air. To most people, it's an ordinary sight. But to Isaac Newton, it was a clue to the secrets of the universe. From that falling apple, Newton imagined invisible forces, gravity, reaching across the heavens. The same pull that brought the apple down kept the moons circling the Earth and the planets circling the sun. Newton's Principia Mathematica, published in 1687, was more than a book of equations. It was a promise. For the first time, it seemed that nature could be fully understood, written in the language of mathematics. Every motion, every orbit, every rise and fall could be described with certainty. If you knew the present, you could predict the future. This belief, later called determinism, became the foundation of classical physics. The universe was a great machine, its parts moving in perfect order. Drop a ball, and the laws of motion would tell you exactly where it would land. Aim a cannon, and mathematics could trace the arc of the cannonball. Even the planets, massive and distant, obeyed Newton's rules. The heavens were not a mystery anymore. They were part of the same mechanical clock. In the 1800s, another set of discoveries added to this confidence. James Clerk Maxwell, a Scottish physicist, unified electricity, magnetism, and light into one sweeping theory. His equations showed that light itself was a wave, an electromagnetic wave rippling through space. Suddenly, phenomena that had once seemed separate, the spark of lightning, the pull of a magnet, the glow of a candle, were bound together. With Newton's laws of motion and Maxwell's equations of electromagnetism, the world seemed almost complete. The two systems could explain almost everything people observed. Engineers used them to build railroads, steamships, and telegraphs. Astronomers used them to chart the skies. Architects used them to build bridges that would not collapse. The machine of the universe was reliable, elegant, and human beings had learned to read its gears. By the late 19th century, many scientists believed they stood at the threshold of final knowledge. The American physicist Albert Michelson, in 1894, declared, "The more important fundamental laws and facts of physical science have all been discovered. The future truths of physical science are to be looked for in the 6th place of decimals. In other words, we already know the laws. All that's left is polishing the details." And for a time, this seemed true. The equations of Newton and Maxwell predicted eclipses, explained tides, powered machines, and lit cities. They worked so well that scientists could almost forget the messy, confusing parts of reality that didn't quite fit. But cracks had already begun to appear. When physicists studied the orbit of Mercury, they noticed it moved in ways Newton's laws could not fully explain. It was as though the planet carried a tiny secret the equations couldn't capture. When they measured the way objects glowed when heated, a problem called blackbody radiation, the predictions of classical physics broke down completely, giving results that were absurd, even infinite. And when they examined light itself more carefully, it began to behave in ways no one expected. Sometimes like a wave, sometimes like a particle. These were small problems at first, but they whispered of something deeper. If Newton's and Maxwell's laws were the whole story, why did the universe resist them at the edges? Still, most scientists at the dawn of the 20th century believed the world was fundamentally classical. If you knew the mass, the position, and the velocity of every particle, you could calculate everything that would ever happen. The universe was like a great billiard table, every collision predictable, every outcome certain. It was a comforting picture, solid, logical, mechanical. The apple falls, the cannonball arcs, the planet circles, and the light ripples. Everything has a cause, and everything follows from that cause with precision. There was no room for mystery, no space for chance. The universe was a grand machine, and humans had nearly read its instructions. And yet in the laboratories of Europe, new experiments were beginning to suggest that this picture was incomplete. What happens when you heat a metal until it glows? Why does light sometimes knock electrons free in ways Maxwell's waves cannot explain? Why do atoms, so small and indivisible, radiate energy in jumps instead of smooth flows? These were not questions the old physics could answer. They were cracks in the machine, hairline fractures in the perfect clockwork. At first, they seemed minor, curiosities at the edge of precision. But within a few decades, those cracks would shatter the old world view entirely, replacing certainty with probabilities, particles with waves, and the familiar with the bizarre. Still, before the storm of quantum mechanics broke, it is worth pausing to feel what the world was like in that age of classical certainty. Imagine being a scientist in 1890. You believe the universe is fully knowable. You believe every effect has a cause that can be measured, every action a reaction that can be calculated. You believe the future is written, if only you could gather enough information. And then imagine, without knowing it, you're standing on the edge of a revolution. The very foundations of knowledge are about to shift, and the solid ground beneath your feet will turn to something far stranger, far less certain, and far more beautiful. This was the world before quantum, a world of apples and orbits, of light as waves, of cause and effect, a world of certainty, a world that was about to end. At the dawn of the 20th century, physics stood proud. Newton's laws guided the planets, Maxwell's equations carried electricity across continents, and engineers used both to reshape daily life. But deep in the laboratories of Europe, a quiet crisis was brewing. It began not with planets or lightning, but with something humble, something ordinary, the glow of heated objects. Every child has seen it. Metal heated until it glows red, then orange, then white. A blacksmith's iron, the coil of an old stove, even the embers of a fire all shift colour as they grow hotter. The phenomenon was simple to witness, yet devilishly hard to explain. Physicists called it the blackbody problem. A blackbody was an idealised object, something that absorbed all radiation and emitted it perfectly, without reflection. Scientists wanted to describe how much light, at which colours, or wavelengths, such a body would emit at different temperatures. The task seemed straightforward. Classical physics had equations for energy, for waves, for heat. Surely they could be stitched together into a complete description. And yet, when they tried, the math went wrong. Very wrong. The classical calculations predicted that as the wavelength of emitted light grew shorter, moving into the ultraviolet range, the intensity of radiation would grow without limit. This meant that a glowing object should pour out infinite energy in ultraviolet light. The prediction was absurd. Experimentally, no such thing happened. Real objects glowed with specific peaks of intensity. They did not flood the world with endless ultraviolet rays. The failure was so glaring that it earned a darkly comic name, the ultraviolet catastrophe. It was in this puzzle that Max Planck, a German physicist, found himself entangled. Planck was not a revolutionary by temperament. He admired order, tradition, and the certainty of classical physics. He once wrote that new theories would be built upon Newton and Maxwell as one might add stones to a cathedral. He never sought to tear the cathedral down, yet in wrestling with the blackbody problem, he would do exactly that. Planck searched desperately for a formula that fit the experimental data. He tried every trick of classical physics, bending equations, rearranging terms. Nothing worked. The theory stubbornly produced infinities where none existed. At last, almost reluctantly, he proposed something radical. Not because he believed it, but because it worked. What if energy was not continuous? What if, instead of flowing smoothly, like water from a tap, energy came in little chunks, little indivisible packets? Planck imagined oscillators, tiny vibrating systems within matter that could not emit energy in arbitrary amounts, but only in multiples of a fundamental unit. He called these units quanta, from the Latin word for how, much. This was a shocking idea. Classical physics said energy was like a smooth continuous curve. You could have as much or as little as you liked, but Planck's formula said no. It came in steps like rungs on a ladder. You could climb from one to another, but never rest in between. When Planck applied this assumption, the catastrophe vanished. His formula fit the experimental curves perfectly. The blackbody spectrum, the way objects glow at different temperatures, was explained at last. For Planck, the discovery was unsettling. He did not yet think quanta were real. To him, they were a mathematical trick, a desperate hypothesis. He once described his theory as an act of desperation. He believed that someday someone would find a way to reconcile the delta with classical physics. But the seed had been planted, and it would not wither. Soon, other problems began to sprout where quanta offered the only answer. The photoelectric effect, light knocking electrons from metal surfaces, defied wave theory until Einstein used quanta to explain it. The stability of atoms, the specific colours of light they absorbed and emitted, the strange behaviours of tiny particles, all would fall into place only if energy came in packets. In hindsight, it is tempting to see Planck's step as the beginning of a grand revolution, the moment the age of classical certainty gave way to quantum strangeness. But in 1900, when he presented his findings, it did not feel that way. The world did not shake, the cathedral did not crumble. Most physicists treated his formula as a curiosity, a stopgap. Even Planck himself clung to the hope that it would someday be absorbed back into classical theory. And yet, history is often written not in thunderclaps, but in whispers. A quiet paper, a reluctant idea, a formula that simply fits the data better. The world rarely notices when the ground first begins to shift beneath its feet. To understand the magnitude of Planck's leap, imagine what it meant. For centuries, energy had been like a smooth highway, continuous and predictable. Now, suddenly, it seemed to be a staircase, discrete and quantized. Nature, at its most fundamental level, was not a flowing river, but a series of jumps. This idea was so alien that even those who accepted it struggled to grasp its meaning. Was energy truly quantized, or was this just a mathematical convenience? Did reality itself come in packets, or was it only our description that did? These questions would echo for decades, but whether or not Planck believed it, the cracks had widened. The old machine of physics, once so solid, was beginning to rattle, and through those cracks came a strange new light, the light of quanta. The birth of quanta was not greeted with celebration. It was greeted with unease, confusion and doubt. Yet without it, nothing that followed, wave-particle duality, uncertainty, entanglement, would have been possible. It was the first tremor of an earthquake that would soon shake the foundations of science, philosophy, and even the way humans thought about reality itself. Planck himself, late in life, would reflect that a new scientific truth does not triumph by convincing opponents, but because its opponents eventually die and a new generation grows up that is familiar with it. His quantum was no exception. It was strange, unsettling, and resisted by many, but it was true, and truth once spoken cannot be silenced. At the turn of the 20th century, Max Planck had introduced a strange idea. Energy comes in little packets, quanta. To him, it was a reluctant trick, a mathematical convenience to fix a broken formula. He never dreamed it would mean that reality itself was quantized, but another mind, sharp, curious and bold, was ready to take that idea and give it a daring interpretation. That mind belonged to Albert Einstein. In 1905, a young Einstein was working at the Swiss Patent Office in Bern, filing away technical documents by day and thinking about the deepest puzzles of the universe by night. That year, he would publish 4 papers that would change physics forever. One of them was on the photoelectric effect, a phenomenon that classical physics could not explain. The photoelectric effect was simple to describe. When light shines on certain metals, electrons are ejected from the surface. Shine enough light, and the metal produces a measurable electric current. In the late 1800s, physicists believed they understood light perfectly. Maxwell had shown it was a wave of electromagnetic fields rippling through space. If light was just a wave, then its intensity, how bright it was, should control how much energy it delivered. Imagine waves crashing on a beach. Larger waves carry more energy. They batter the shore more fiercely. By analogy, physicists thought a brighter beam of light stronger waves, should knock electrons out of a metal more easily. If you kept shining weak light long enough, eventually, the electrons should gather enough energy to escape. But experiments showed otherwise. When light of the right frequency, the right colour, hit a metal, electrons flew out instantly, no matter how faint the beam. A dim violet light could eject electrons at once, while a blazing red light, though more intense, did nothing. The brightness didn't matter. The colour did. Even more strangely, the ejected electrons carried specific amounts of energy, determined not by the brightness of the light but by its frequency. Classical wave theory had no answer for this. It predicted that energy should build up gradually, like water filling a bucket, until the electron had enough to escape. But the electrons didn't wait. They leapt out immediately, as if the energy had struck them in one sudden blow. Einstein saw the problem and proposed a radical solution. What if light itself wasn't just a wave? What if light came in quanta, just as Planck had suggested energy did? Each quantum would carry a specific amount of energy, determined by the light's frequency. A single quantum could strike an electron and knock it free in an instant. Einstein called these quanta of light Lichtquanten. Today we call them photons. A photon was not a wave spread smoothly across space. It was a discrete packet of energy, a particle of light. Its energy was given by a simple equation. E equals hf, E equals h, fe equals hf, where E is the energy, FFF is the frequency of the light, and HHHH is Planck's constant, the same constant that had appeared in the blackbody formula. The higher the frequency, the more blue the light, the greater the energy of each photon. With this picture, the photoelectric effect suddenly made sense. A low-frequency red photon simply didn't carry enough energy to knock an electron free, no matter how many red photons struck the metal. But a high-frequency violet or ultraviolet photon had enough energy in a single strike. The electron was ejected immediately, without waiting for energy to build up. Einstein's interpretation was bold because it turned centuries of certainty on its head. Since the days of Maxwell, light had been understood as a wave. The evidence seemed overwhelming. Light diffracted, refracted, interfered, all behaviours of waves. To say that light was made of particles sounded like regression, back to Newton's old corpuscular theory of light that had been discarded a century before. But Einstein was not claiming that light was only a particle. He was saying something stranger. Light behaved both as a wave and as a particle, depending on how you looked at it. Sometimes it spread and interfered like a wave. Sometimes it struck and ejected electrons like a particle. Reality was not one or the other, but both. This idea was not welcomed easily. Planck himself, though grateful for Einstein's insight, resisted the notion that light was truly made of particles. Many physicists dismissed the photon concept as too radical, preferring to cling to wave theory. It would take decades and further experiments for the scientific community to fully accept Einstein's view. Yet the evidence kept mounting. Experiments showed that electrons ejected in the photoelectric effect had energies exactly predicted by Einstein's photon formula. No wave theory could reproduce the results. The particle nature of light had to be real. Einstein's photons carried consequences far beyond the photoelectric effect. They meant that the most familiar thing in the world, sunlight itself, was not what it seemed. A warm ray of light on your face was not a continuous wave, but a rain of tiny quanta, each carrying its own packet of energy. The sun was not pouring out waves alone. It was sending trillions upon trillions of photons across space, streaming to Earth. The implications were staggering. If light was both wave and particle, then the old categories of thought were broken. Reality could not be, explained by simple labels. Something deeper, more paradoxical, was at play. Einstein's insight would also spark technology. The photoelectric effect became the foundation of solar cells, photodiodes, and many sensors we rely on today. The idea that light could deliver energy in discrete packets shaped electronics, lasers, and even modern communication. What began as a strange puzzle in a physics lab would one day power the world. And for Einstein himself, this work was foundational. Though he would later become more famous for relativity, it was his explanation of the photoelectric effect that won him the Nobel Prize in Physics in 1921. The committee hesitated to reward relativity, still controversial at the time, but the photon was undeniable. The photon changed not only physics but philosophy. It shattered the neat picture of waves and particles as separate categories. It suggested that reality was richer, stranger, and less intuitive than the human mind had imagined. To say light is both wave and particle was not to solve the mystery, but to live with it, to accept that the truth might not fit our old ways of thinking. And if light, the most familiar, the most visible thing in the universe, was this strange, what else might be? Einstein had not only explained a stubborn puzzle, he had cracked the door to a new world, one where certainty gave way to duality, and where the very fabric of reality behaved in ways no one had dreamed. By the early 20th century, the world of physics had already been shaken. Planck had shown that energy comes in quanta. Einstein had shown that light, long thought to be a wave, could also act like a particle, the photon. It was unsettling enough to imagine beams of sunlight as showers of invisible particles raining down upon the Earth. But then came an even stranger thought. If waves can act like particles, could particles act like waves? This daring idea came from a young French aristocrat, Louis de Broglie, in the 1920s. De Broglie was not a traditional physicist by training. His early studies leaned toward history and philosophy. But the mysteries of the quantum age drew him in, and he began to wonder about the symmetry of nature. Einstein had shown that light had a dual identity, sometimes wave, sometimes particle. De Broglie asked a simple, radical question. Why should light be special? If light, once thought a pure wave, also had particle-like properties, might matter, once thought pure particle, also have wave-like properties? It was a breathtaking reversal. Imagine looking at a stone in your hand, solid and weighty. Classical physics told you it was a particle, a lump of matter with definite size and mass. Waves were for ripples on water, for sound in air, for light in space. But de Broglie dared to suggest that the stone, and the atoms within it, might also possess waves. Not metaphorical waves, but real, physical ones. He gave these waves a name, matter waves. De Broglie proposed that every particle of matter, whether an electron, a proton, or even larger objects, has a wavelength associated with it. The formula was simple, echoing Einstein's photon equation. Lambda equals h over p, where lambda is the wavelength, h is Planck's constant, and ppp is the particle's momentum. This meant that the smaller and lighter a particle was, the more noticeable its wave-like behaviour would be. For everyday objects, a baseball, a car, a human being, the wavelength was unimaginably tiny, so small that no experiment could ever detect it. But for electrons, the lightweight particles inside atoms, the wavelength was significant. The idea seemed almost absurd. Could an electron, a particle with mass and charge, really spread out like a wave? Could it interfere, diffract, ripple? De Broglie thought so. At first his idea was theory alone, but theories live or die by experiment, and within a few years, experiments gave de Broglie his vindication. In 1927, Clinton Davison and Lester Germer, two physicists in the United States, performed an experiment in which they fired a beam of electrons at a crystal of nickel. To their astonishment, the electrons scattered not like bullets but like waves. They formed interference patterns, bright and dark bands, just like light passing through a diffraction grating. It was the proof. Matter, at its most fundamental, behaved like waves. This discovery shook the very foundations of reality. The categories that had seemed so solid, wave and particle, matter and energy, were dissolving. Everything was both, depending on how you looked. Electrons could orbit an atom as if they were waves wrapped around a nucleus, forming standing patterns of probability. At the same time, they could strike a screen like tiny particles, leaving single dots. The implications were enormous. Atoms, once imagined as miniature solar systems with electrons orbiting like planets, had to be reimagined. If electrons were waves, then only certain standing wave patterns were stable around the nucleus. This explained why atoms emitted light at specific colours. The electrons could only jump between these allowed wave states. Suddenly, the strange spectral lines observed in experiments made sense. The atom was not a solar system at all, but a vibrating symphony of matter waves. De Broglie's vision also expanded the meaning of quantum mechanics. It was not just a theory about light, nor even about electrons. It was a theory about everything. All matter has wave-like properties, from the smallest electron to the largest object. We do not notice these waves in our daily lives because Planck's constant is so small. For large, heavy objects, the wavelength shrinks into invisibility. But at the microscopic scale, where atoms and electrons rule, the waves are undeniable. The beauty of de Broglie's insight lay in its symmetry. Light had been forced to surrender its identity as purely a wave. Matter had been forced to surrender its identity as purely a particle. At the quantum level, nature no longer respected our categories. Everything, light, matter, energy, was both particle and wave. Einstein himself admired de Broglie's courage. It was not enough to observe strangeness. One had to imagine a universe strange enough to contain it. For his work, de Broglie would later win the Nobel Prize in Physics, his single great insight forever altering the course of science. To modern ears, wave-particle duality may sound almost familiar, a phrase repeated in classrooms and documentaries. But to the scientists of the 1920s, it was like saying the Earth was both round and flat at the same time, or that fire was both hot and cold. It defied intuition, tore at logic, and yet the evidence demanded belief. Wave-particle duality was more than a puzzle. It was a crack in reality itself. If electrons could be waves, where did the wave exist? In space? In the electron itself? And if matter could spread out as a wave, what did that mean for the concept of a single, localized particle? These questions would haunt physicists and lead to the creation of the mathematical heart of quantum mechanics, the Schrödinger equation. But that lay ahead. For now, the world had changed once again. The boundaries between categories had blurred. Waves were particles, particles were waves, and the solid, dependable matter of the universe had revealed itself to be far more fluid, far more mysterious than anyone had dreamed. The age of certainty was gone. The age of quantum had begun. By the 1920s, scientists had accepted a strange truth. Light behaved as both a wave and a particle, and matter too could act like a wave. The theories were daring, the mathematics elegant. But nothing could prepare the world for the shock of seeing this duality play out in a single simple experiment, one that remains, to this day, the most haunting demonstration of quantum mechanics. It began not in the age of quantum, but much earlier. In 1801, the English scientist Thomas Young performed an experiment with light. He passed a beam of sunlight through two narrow slits cut into a card and let it fall on a screen. If light were made of particles, Young expected to see two bright spots, like twin beams shining through. But instead he saw something different. A series of bright and dark bands, an interference pattern. It was the signature of waves. Just as ripples on a pond overlap and create patterns of peaks and troughs, light waves overlapped and interfered. Where two peaks met, they made a bright band. Where a peak met a trough, they cancelled, leaving darkness. Young's experiment was hailed as proof that light was a wave, and it stood as triumph for more than a century. But in the 20th century, as Einstein's photons and de Broglie's matter waves entered the stage, physicists asked, what happens if we repeat Young's experiment in this new world of quanta? They did, and the results still echo in wonder and confusion. When a beam of electrons, just matter, solid particles, is fired through a double slit, something remarkable happens. Instead of forming two clumps on the screen, as bullets would, the electrons form the same interference pattern that Young had seen with light. Bright and dark stripes emerge, as though the electrons are waves interfering with themselves. Matter behaves like light. But the strangeness goes deeper. Physicists wondered, perhaps the interference pattern appears only when many electrons are fired at once, their waves mingling with each other. So they tried firing the electrons one at a time, separated by long intervals. Each electron should pass through one slit or the other, like a tiny bullet, and land as a single dot. At first, that's what the screen shows, scattered dots. But as more and more electrons are sent through, a pattern emerges. The dots, random at first, build up into the same interference bands. Each electron alone behaves like a wave. It passes through both slits at once, interferes with itself, and only when it strikes the screen does it appear as a particle. Think about that for a moment. A single particle, with mass and charge, takes two paths simultaneously. It behaves as though it is spread out like a wave, until the moment we look, and then, in that instant, it is localized again, a single dot on the screen. The experiment seemed to mock common sense. How could something be in two places at once? How could a particle interfere with itself? What was the wave that guided its behaviour? These questions burned through the minds of physicists, and the answers only deepened the mystery. For the interference pattern vanishes if we try to observe the slits directly. When detectors are placed to see which slit the electron goes through, the pattern of bands disappears. Instead, the electrons behave like particles again, forming two clumps behind the slits. It is as if the act of measurement forces reality to choose, particle or wave, one path or both. Observation itself alters the outcome. This is the heart of the measurement problem in quantum mechanics. The electron is not simply a particle or a wave until we measure it. It exists in a strange state of superposition, both possibilities alive until the act of observation collapses it into one. The double slit experiment has been repeated countless times, with light, with electrons, even with entire atoms and molecules. The result is always the same: interference when unobserved, particles when observed. Nature seems to ask us, what does it mean to look? What does it mean to measure? To physicists like Richard Feynman, the double-slit experiment became the perfect symbol of quantum mechanics. He once said, "It contains the only mystery. We cannot make the mystery go away by explaining how it works." For in this single experiment, all the strangeness of quantum reality is laid bare. For the Greeks, of old, reality was made of earth, air, fire and water. For Newton it was made of particles and forces, for Maxwell of waves and fields. But the double-slit experiment tells us something far stranger. Reality is not what it seems until we look. Between observation and outcome lies a realm of possibility, where particles are waves, where paths are taken and not taken, where the world is less solid than we imagine. And yet, despite its strangeness, the double-slit experiment is not merely a philosophical puzzle, it is also the foundation of quantum technology. The very principles that allow interference also allow the design of electron microscopes, lasers, and quantum computers. The mystery has practical teeth. Still, its lesson is profound. When we drop a stone into a pond, we expect ripples. When we throw a stone at a wall, we expect it to hit or miss. But at the quantum level, stones are ripples and ripples are stones, and the act of watching changes what we see. The double-slit experiment stands as a reminder that the universe is not a machine of certainty, ticking along like a clock. It is a fabric of probabilities, woven with threads we do not yet fully understand. And every time a particle passes through those two slits, it carries with it the whisper of a deeper reality, one that challenges not only our physics, but our very sense of what is real. By the mid-1920s, the quantum world was no longer a collection of oddities. It was becoming a new science, full of daring experiments and radical ideas. Electrons behaved like waves. Light was both particle and wave. The double-slit experiment had shown that reality itself seemed to wait until observation before revealing its face. And into this swirling mystery stepped a young German physicist with a sharp mind and a gift for clarity, Werner Heisenberg. Heisenberg was only in his mid-20s when he made his great leap. Restless and brilliant, he was part of the circle of thinkers, Niels Bohr, Erwin Schrödinger, Max Born, who were trying to make sense of quantum behaviour. What exactly was an electron in an atom? Was it a wave, a particle, or something else entirely? How could mathematics describe it? Heisenberg's insight was simple, but devastating. He realised that the problem was not just in how we described electrons, but in what could ever be known about them. In the world of Newton, certainty was a given. If you knew the position of a particle, where it was, and its momentum, how fast and in what direction it was moving, you could calculate its future with perfect accuracy. The present contained the seeds of the future. Determinism reigned. But Heisenberg showed that in the quantum world this dream collapsed. You could not know both position and momentum with perfect precision. The more carefully you measured one, the fuzzier the other became. This was not a flaw of instruments, not a failure of microscopes or rulers, it was a law of nature itself. Heisenberg expressed this in what became known as the uncertainty principle. Delta x delta p greater than or equal to h divided by 4pi. Here, delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to 1 divided by 4 pi. Delta was delta p greater than or equal to O divided by 4 pi. Delta was delta p greater than or equal to h divided by 4 pi. Delta was delta O greater than or equal to h divided by 4 pi. Delta was delta p greater than or equal to O divided by 4 pi. Delta was delta p greater than or equal to r divided by 4 pi. Delta x delta p greater than or equal to r divided by 4 pi. Delta was delta p greater than or equal to r divided by 4 pi. Delta bar delta p greater than or equal to r divided by 4 pi. Delta ras delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to r divided by 4 pi. Delta x delta p greater than or equal to r divided by 4 pi. Delta x delta p greater than or equal to h divided by 4 pi. Delta x delta p greater than or equal to sh divided by 4 pi. Delta x delta p greater than or equal to sh divided by 4 pi. delta x delta p greater than or equal to WSR divided by 4 pi, delta x delta p greater than or equal to h divided by 4 pi, delta x delta p greater than or equal to h divided by 4 pi, delta x delta p greater than or equal to h divided by 4 pi, delta x delta p greater than or equal to h divided by 4 pi, delta x delta p greater than or equal to h divided by 4 pi, delta x delta p greater than or the uncertainty in position, and delta p the uncertainty in momentum. Their product can never be smaller than a fixed limit given by Planck's constant. This meant that at the quantum level, particles do not have sharp, definite paths the way billiard balls do. An electron does not move like a tiny planet around a nucleus. Instead, it exists as a cloud of possibilities, a blur of potential positions and momenta. When we try to pin it down, it resists, slipping away in one aspect as we grasp the other. It was a shocking blow to classical intuition. For centuries, physicists had believed that uncertainty was only temporary, a matter of incomplete information. If we had better instruments, more data, finer measurements, we could in principle know everything. But Heisenberg's principle said no. Uncertainty was built into reality. It was not ignorance, it was existence. Imagine trying to photograph a hummingbird's wings. The faster your shutter, the clearer the wing's position, but the blurrier its speed. Slow down the shutter, and you capture the motion, but the position smears. At the quantum scale, this is not a matter of cameras, but of being. An electron is partly wing and partly blur, and the universe refuses to reveal both sharply at once. The implications were enormous. If position and momentum could not be known simultaneously, then the dream of predicting the future with perfect accuracy collapsed. Determinism, the proud child of Newtonian physics, was dethroned. The quantum world was a world of probabilities, not certainties. Niels Bohr, Heisenberg's mentor, embraced this truth. He argued that physics was no longer about describing how reality is, but only what we can say about it. Atoms did not have fixed orbits. They had probability clouds. Measurements did not reveal pre-existing properties. They brought those properties into being. Not all agreed. Einstein, famously, resisted. God does not play dice, he said, unwilling to accept a universe where chance was fundamental. To him, uncertainty was a sign of an incomplete theory, not a final truth. But experiment after experiment confirmed Heisenberg's principle. The dice, it seemed, were real. The uncertainty principle was not just philosophy, it explained real features of the world. Atoms, for example, are stable because electrons cannot be confined too tightly to the nucleus. If their position were perfectly sharp, their momentum would become infinitely uncertain, and they would fly away. Instead, the uncertainty principle forces a balance, creating the fuzziness that holds atoms together. Without uncertainty, matter itself would not exist. It also explained phenomena like zero-point energy, the fact that even in absolute darkness, particles still jiggle, never entirely at rest. The principle prevents the universe from being perfectly still. At the quantum level, motion and uncertainty are eternal companions. Heisenberg's principle also reshaped how physicists thought about knowledge itself. It drew a line, sharp and unyielding, around what can be known, not because of human weakness, but because of the structure of reality. There are questions the universe will not answer, not now, not ever. To live in a Newtonian universe was to live in a world of certainty, where the future was simply the past written forward. To live in a Heisenbergian universe was to live in a world of mystery, where probabilities ruled, where chance and uncertainty were not illusions but truths. The shift was not easy. Even today, the uncertainty principle can sound like an abstraction, a technicality of mathematics. But it is more than that. It is a reminder that the universe is stranger than our logic, that reality has depths we cannot pin down. And yet out of this uncertainty came stability, creativity, and even beauty. Atoms, molecules, chemistry, and life itself are shaped by quantum fuzziness. If the universe were rigid, deterministic, and certain, it might also be sterile. Instead, uncertainty gives rise to possibility. Werner Heisenberg, still a young man when he made this discovery, later reflected on the philosophical weight of his work. What we observe, he said, is not nature itself. but nature exposed to our method of questioning. The uncertainty principle was not just a scientific law, but a lesson in humility. It told us that there are limits to what we can know, and that within those limits lies the heart of reality itself. By the mid-1920s, quantum theory was still a patchwork of ideas. Planck had introduced the quantum, Einstein had given us the photon, de Broglie had argued that matter itself could act like a wave. Heisenberg had declared that uncertainty was built into nature. Each piece was striking, but there was no single framework to tie them all together. What quantum physics needed was its own version of Newton's laws or Maxwell's equations, a guiding principle, a master equation. And that task fell to a brilliant Austrian physicist named Erwin Schrödinger. Schrödinger was not just a scientist. He was a thinker drawn to philosophy, art and beauty. For him, physics was not only about equations, but about clarity and elegance. In 1926, while retreating to the quiet of the Swiss Alps, he began working on a new way to describe the strange behaviour of electrons. His inspiration came from Louis de Broglie's radical proposal that electrons behaved like waves. If that was true, Schrödinger reasoned, there should be a mathematical law, a kind of wave law, that described how these matter waves moved and changed. Just as the vibrations of a guitar string could be predicted by a wave equation, so too could the vibrations of an electron. And that is exactly what Schrödinger created, a single, powerful equation that described how these quantum waves evolve over time. Today we call it the Schrödinger equation, and it is the beating heart of quantum mechanics. But what does it actually say? At the centre of Schrödinger's equation is a strange new idea called the wave function. The wave function is not a physical wave you can see, like ripples on water. Instead, it is a kind of invisible wave of possibility. It tells us where a particle, like an electron, is likely to be. If you imagine an electron not as a point but as a blurry cloud, the wave function describes the shape of that cloud, where the particle might show up if we go looking. Schrödinger's equation tells us how that wave function changes with time. In other words, it is the rulebook for how probabilities shift and flow in the quantum world. To see how powerful this is, think of the simplest atom, hydrogen, with one electron circling a single proton. Classical physics struggled with hydrogen. If the electron really orbited like a planet around a sun, it should lose energy, spiral inward, and collapse into the nucleus. But that never happens. Atoms are stable. Why? Schrödinger's equation gave the answer. The electron is not a tiny planet at all. It is a wave, wrapped around the nucleus. Only certain wave patterns are stable, and those stable patterns correspond to specific energy levels. This explained the strange discrete colours of light emitted by hydrogen, the spectral lines that had puzzled scientists for decades. They were not accidents. They were the fingerprints of quantum waves. Suddenly the atom was no longer a mystery. It was a symphony of standing waves, with electrons vibrating in harmony, locked into stable arrangements. The equation didn't just solve hydrogen, it laid the foundation for all of chemistry. Why atoms bond into molecules, why some substances conduct electricity while others insulate, why life's complex molecules form the way they do. All of it emerges from Schrödinger's law. But while the mathematics was beautiful, it also carried unsettling implications. The wave function did not give certainty. It did not tell us where an electron is, only the probabilities of where it might be found. When we measure, the wave of possibilities collapses into a single outcome, a dot on a screen, a particle detected. Between measurements, the electron exists as a cloud of chance, neither here nor there, neither one path nor the other. This was the beginning of what became known as the measurement problem. Schrödinger's equation described a smooth, continuous wave of probability, but whenever we looked, reality snapped into something definite. How did that happen? Did the wave collapse because of observation? Was it our consciousness that forced reality to choose? Or was the wave just a tool for prediction, not something real at all? These questions haunted Schrödinger. He loved the clarity of his equation but disliked the ghostly nature of the wave function. To him, the idea that reality itself was smeared out until an observer forced it to become definite felt absurd. Later, he would dramatize this discomfort with a thought experiment that became famous: a cat trapped between life and death inside a box. Yet, whether or not he liked its interpretation, Schrödinger's equation worked. It worked with astonishing accuracy. It explained the behaviour of atoms, molecules and light. It became the cornerstone of quantum mechanics, the most successful scientific theory in history. And its impact went far beyond physics. It shaped the modern world. Every laser pointer, every semiconductor chip, every medical scanner, every solar panel owes its existence to the Schrödinger equation. Without it, there would be no computers, no smartphones, no internet. The quiet work of an Austrian physicist in the 1920s underpins the entire technological civilization of the 21st century. Still, beyond the technology, there is something deeply poetic in Schrödinger's law. It tells us that reality is not solid and predictable, but fluid and uncertain. It tells us that particles are not little billiard balls, but waves of probability. It tells us that at the deepest level, the universe is not a machine, but a kind of cosmic music, resonating with hidden harmonies. For Schrödinger, who sought beauty in ideas, it was a triumph. He had given quantum mechanics its central law, its unifying language. He had shown that the atom was not chaos but order, not collapse but stability. And yet, in doing so, he had also revealed that certainty was gone forever. The Schrödinger equation gave physics not just a tool, but a worldview where chance and probability are fundamental, where reality is not fixed until we measure it, and where the act of observation itself plays a role in shaping the outcome. It was the equation that turned quantum theory from a collection of mysteries into a coherent science, and it remains to this day the equation that describes the hidden waves behind everything you see. By the late 1920s, quantum mechanics had transformed physics. Schrödinger's equation gave a powerful description of how quantum waves evolve, but along with its beauty came a deep unease. If the wave function described a spread of possibilities, then what was real before we looked? Did an electron truly exist in a blur of locations until we measured it? Did the world only become definite when observed? These questions troubled Erwin Schrödinger himself. He had written the very equation that defined the quantum wave, but he was never entirely comfortable with its implications. To him, it seemed absurd to imagine that something could be both one thing and another until someone checked. To dramatise his unease, Schrödinger imagined a thought experiment in 1935, one that would become famous far beyond the halls of physics. He imagined a cat, picture it, a sealed steel box closed so tightly that no sound, no sight, no signal can escape. Inside sits a living cat. Alongside it is a small device, a vial of deadly poison, a hammer, and a detector connected to a single atom. The atom is unstable, with a 50% chance of decaying within an hour. If it decays, the detector triggers the hammer, which shatters the vial, releasing the poison, killing the cat. If the atom does not decay, the cat lives. Now here is the twist. According to quantum mechanics, before we open the box, the atom is not simply decayed or not decayed. It exists in a state of superposition, both possibilities alive at once. If the atom is in superposition, then so is the entire setup. The poison is both released and sealed. The cat is both dead and alive. In the eerie logic of quantum mechanics, until the box is opened, the cat is not one thing or the other. It is both, smeared across two contradictory states, suspended between life and death. Schrödinger proposed this not because he believed it, but to show how bizarre the implications of quantum theory had become. For electrons or photons, superposition seemed strange but manageable, but for a cat, a warm breathing creature, the idea felt absurd. Surely the cat is either alive or dead, regardless of whether anyone looks. Surely reality does not wait for our eyes to decide. And yet, the mathematics of quantum mechanics seem to demand exactly that. This paradox, known as Schrödinger's cat, became a symbol of the measurement problem. What does it mean for something to exist in superposition? Is it real, or is it just a mathematical convenience? When does the wave of probabilities collapse into a single outcome? Is it at the level of atoms or molecules or cats, or only when consciousness enters the picture? Physicists debated fiercely. Niels Bohr argued that quantum mechanics did not describe reality itself, but only the results of experiments. For him, asking about the cat before opening the box was meaningless. Others, like Einstein, rejected this, insisting that the cat must have a definite state whether or not we observe it. To Einstein, the cat paradox was proof that quantum theory was incomplete, that some hidden variables must exist to restore certainty. but experiments kept showing that superposition was not just a trick of mathematics. In laboratories, scientists began creating superpositions not just of atoms, but of larger and larger systems, molecules, currents of electrons, even tiny mechanical devices. The line between quantum and classical, between wave and reality, grew blurrier. Schrödinger's cat also became a cultural icon, escaping the confines of physics. Philosophers, artists, and writers seized on the image of a creature both dead and alive as a metaphor for ambiguity, paradox, and the hidden nature of truth. It entered popular culture as shorthand for the strangeness of the quantum world. But behind the humour and metaphor lies a genuine puzzle. What does it mean for something to exist in superposition? If a photon can be both here and there, if an electron can take two paths at once, what is reality before we measure it? Does the universe split into branches, with the cat alive in one world and dead in another, as some interpretations suggest? Or does the act of observation itself collapse the wave into one outcome? The cat forces us to confront the gap between the microscopic and the macroscopic, between theory and intuition. At the scale of atoms, superposition is undeniable. At the scale of cats, it feels impossible. And yet the laws are the same. Where exactly does the quantum blur sharpen into classical certainty? Even today, nearly a century later, there is no final answer. Competing interpretations of quantum mechanics offer different visions. The Copenhagen interpretation, favoured by Bohr, says that the wave function is only a tool for prediction, not a real physical thing. The many worlds interpretation, proposed later by Hugh Everett, says that every possibility is real, and the universe branches into parallel realities. In one, the cat lives, in another, it dies. Other interpretations suggest hidden variables or decoherence, or even the role of consciousness. But Schrödinger's cat remains the perfect symbol of the mystery. It takes the abstract mathematics of the quantum and drags it into the everyday world. It asks us to imagine a living creature in a state of impossible limbo, and in doing so it forces us to admit how little we truly understand. And perhaps that is the point. Schrödinger did not mean his cat to be taken literally. He meant it as a challenge, a way of saying, look how strange our equations have become. If this is what the mathematics says, then surely we have not yet understood the full story. Yet, paradoxically, the cat has endured not because it solved the puzzle, but because it revealed it so vividly. It shows us that quantum mechanics is not just about equations and experiments. It is about the very nature of reality, about whether the world exists independently of our observation, or whether it waits for us to look. In the quiet imagination of Schrödinger, a cat was trapped in a box. In the imagination of the world, that cat has never escaped. It sits there still, alive and dead, a symbol of mystery, reminding us that the universe is stranger than our common sense, and that sometimes the deepest truths are the ones we cannot resolve. By the mid-1920s, quantum mechanics had revealed a world stranger than anyone expected. Particles behaved like waves. Waves struck like particles. The double-slit experiment showed matter interfering with itself, while Heisenberg's principle declared that certainty was forever out of reach. Schrödinger's wave function seemed to describe possibilities rather than realities, leaving the unsettling question, what is real before we look? It was in this swirl of confusion that two of the most influential figures of quantum physics, Niels Bohr and Werner Heisenberg, shaped what became known as the Copenhagen interpretation. Bohr, a Danish physicist with a calm, philosophical demeanour, was the elder statesman of quantum theory. Heisenberg, brilliant and young, had just formulated the uncertainty principle. Together, working in Copenhagen in the late 1920s, they tried to provide not only equations, but meaning. Their interpretation was bold, pragmatic, and deeply unsettling. At its heart, the Copenhagen interpretation declared that the wave function, Schrödinger's elegant cloud of probability, was not a description of physical reality itself. It was only a tool for predicting the outcomes of experiments. In other words, the wave function does not tell us what is. It tells us what we are likely to see when we measure. According to Bohr, asking what an electron really is before we measure it is meaningless. Is it a particle? A wave? Both? Neither. For Bohr, these were the wrong questions. Physics, he argued, is not about describing reality as it is in itself. but about describing what we can say about nature through experiments. This idea was called complementarity. A quantum system can show particle-like behaviour in one experiment and wave-like behaviour in another. Both descriptions are true, but they cannot be applied at the same time. They are complementary, not contradictory. Imagine light. In one experiment it produces an interference pattern, proving it is a wave. In another it knocks electrons free instantly, proving it is a particle. Which is it? For Bohr it is both, but which face it shows depends on how we ask the question. The experiment defines the reality we observe. Heisenberg's uncertainty principle fit perfectly into this picture. We cannot know position and momentum with unlimited precision because the very act of measurement disturbs the system. Measurement is not passive. It is an interaction, shaping the outcome. This was the central claim of Copenhagen. Quantum objects do not have definite properties until they are measured. Before measurement, they exist only as possibilities, encoded in the wave function. The act of observation collapses those possibilities into a single outcome. Reality crystallizes only when we look. To many, this was both brilliant and deeply troubling. It seemed to suggest that the observer played a special role in reality, that the world at its core was not independent of our questions, but somehow tied to them. Einstein in particular bristled at this. He famously quipped, "Do you really believe the moon is not there when you're not looking at it?" For Einstein, the Copenhagen view was unsatisfying, even dangerous. He insisted that the cat in Schrödinger's box must be either alive or dead, whether we look or not. To him, quantum mechanics was incomplete, a temporary scaffolding that would someday be replaced by a deeper, deterministic theory. But Bohr stood firm. Again and again, in debates with Einstein, he argued that quantum mechanics was not incomplete. It was complete, but in a new way. It did not describe hidden certainties. It described probabilities, and those probabilities were the fabric of reality itself. For Einstein, God did not play dice. For Bohr, not only did God play dice, but those dice were the fundamental grammar of the universe. The Copenhagen interpretation was not without problems. Critics pointed out that it seemed to treat measurement as a mystical act, dividing the world into the quantum and the classical. Where, exactly, does the collapse occur? When the photon hits the detector? When the detector sends a signal? When a human looks at the data? Copenhagen did not answer. It simply insisted that physics is about results, not hidden realities. Yet despite its vagueness, Copenhagen worked. It allowed physicists to calculate with astonishing accuracy. It explained the stability of atoms, the behaviour of molecules, the interaction of light and matter. It predicted outcomes that matched experiment again and again. For a working scientist, it was enough. Shut up and calculate became the unofficial motto of quantum mechanics. But for philosophers, and for those who sought a deeper understanding, Copenhagen left unease. It seemed to dodge the question of what reality is. Was the wave function real, or just information? Was collapse a physical process, or merely a shift in knowledge? Were we to accept that nature itself was silent on what exists before we measure? And yet, for decades, Copenhagen ruled. It was taught in textbooks, accepted in laboratories, and defended by the giants of the field. Other interpretations would arise, hidden variables, many worlds, pilot waves, but none would dethrone Copenhagen as the mainstream view. Part of its endurance lay in Bohr himself. He had a gift for wrapping mystery in calm authority. To him, the strangeness of quantum mechanics was not a flaw, but a feature. It forced humility, reminding humans that we are not detached spectators, but participants in the unfolding of reality. In this sense, Copenhagen was less a solution than a stance, a way of living with uncertainty. It did not erase the paradoxes, it accepted them. It said, this is how the world works, whether it matches our common sense or not. And so, in the heart of the 20th century, physics embraced a view of reality unlike anything before. The universe, at its smallest scale, was not a machine running independently. It was a dance of possibilities, collapsing into facts only when asked the right question. The Copenhagen interpretation gave quantum mechanics its philosophy, practical, unsettling and enduring. It told us that nature is not what it is, but what it shows us when we measure. And that lesson, as simple as it sounds, continues to echo as one of the most profound shifts in human thought. the realization that reality, at its core, is inseparable from the questions we ask of it. By the 1930s, quantum mechanics had triumphed. Schrödinger's wave equation explained atoms and molecules. Heisenberg's uncertainty principle reshaped our understanding of knowledge itself. Bohr's Copenhagen interpretation gave the theory a philosophy. Quantum systems do not have definite properties until measured. Everywhere scientists looked, experiments confirmed the predictions. But one man remained unconvinced. Perhaps the greatest physicist of them all, Albert Einstein. Einstein had been one of the founders of quantum theory. His explanation of the photoelectric effect introducing photons was a cornerstone of the field. But as quantum mechanics matured, Einstein grew increasingly troubled. The more he saw, the more he believed that the theory was incomplete. For Einstein, the idea that particles existed in a fog of probabilities until someone looked was intolerable. He had spent his life uncovering deep, elegant laws: relativity, gravity, the constancy of the speed of light. To him, the universe was not chaos. It was order, waiting to be discovered. When confronted with Bohr's vision of a universe where chance was fundamental, Einstein objected with a line that became famous: God does not play dice. He did not mean God in a religious sense. He meant that the universe, in its deepest structure, could not be ruled by randomness. There had to be hidden laws beneath the surface, unknown variables that determined the outcome. Quantum mechanics, brilliant as it was, could only be a partial description, a shadow of the full truth. The debates between Einstein and Bohr became legendary. At conferences in the late 1920s and early 1930s, the two giants faced off again and again. Einstein would present a thought experiment meant to show the absurdity of quantum mechanics. Bohr, quick and sharp, would respond, showing how quantum principles survived the challenge. One famous exchange went like this. Einstein proposed a device that could measure both the energy and the timing of a photon with perfect accuracy, something forbidden by the uncertainty principle. If such a device were possible, it would expose quantum mechanics as inconsistent. Bohr, after a sleepless night, returned with a counter-argument. Einstein's device itself would be subject to the uncertainty principle. The laws of quantum mechanics held firm. Bohr often emerged the victor, at least in the eyes of the younger generation. But Einstein was not defeated. He continued to push back, not with experiments, but with ideas. His most famous challenge came in 1935, in a paper written with two collaborators, Boris Podolsky and Nathan Rosen. Together, they presented what became known as the EPR paradox. Einstein, Podolsky and Rosen asked, what if two particles are created together in such a way that their properties are linked? For example, their momenta or their spins might be correlated. If one is measured, the other must have the opposite value to conserve the total. Now, if these two particles are separated, even by great distances, what happens when one is measured? According to quantum mechanics, before measurement, each particle exists in a superposition of possibilities. But when one particle is observed, its wave function collapses, instantly determining the outcome. And if the other particle's state is linked, then it too must collapse, no matter how far away. Einstein saw this as absurd. He called it spooky action at a distance. To him, it violated the principle that nothing could travel faster than light, not even information. If measuring one particle instantly determined the other, across space, then quantum mechanics could not be telling the full story. There must be hidden variables, local causes, underlying laws that explain the results without magic or spookiness. The EPR paper concluded that quantum mechanics was incomplete. The theory worked, yes, but it was not the final word. There had to be a deeper theory, one that restored realism and determinism. Bohr unsurprisingly disagreed. He argued that the EPR paradox did not expose a flaw, but rather highlighted how deeply quantum mechanics changed our notions of reality. For Bohr, there was no need to imagine hidden variables. The paradox only showed that entangled particles were a single system, no matter how far apart. Measuring one did not send information to the other. It simply revealed a property of the whole. The debate raged, unresolved. Einstein could not accept that reality itself was probabilistic, that particles had no properties until measured, that nature rolled dice. Bohr accepted it, embraced it even, and urged others to do the same. For decades, the question lay unresolved. Was Einstein right? that hidden variables waited to be discovered? Or was Bohr right that quantum mechanics was complete as it stood? Ironically, experiments many decades later would test exactly this question. Physicists like John Bell in the 1960s and Alain Aspect in the 1980s designed ways to probe entanglement directly. The results overwhelmingly confirmed quantum mechanics and ruled out many forms of hidden variable theories. The spooky action Einstein hated turned out to be real. And yet, Einstein's rebellion was not in vain. His refusal to accept Copenhagen's easy answers kept the philosophical questions alive. His challenges forced physicists to think more deeply about what quantum mechanics really means. Even today, debates about interpretation trace their roots to those nights when Einstein and Bohr argued across a table, each convinced of his truth. Einstein's rebellion reminds us that even the greatest theories must be questioned, that even overwhelming success can leave room for doubt. He did not live to see the experiments that confirmed entanglement, but his skepticism remains a vital part of the story, a reminder that science is not just about equations, but about meaning. For Bohr, the universe was possibilities collapsing into facts when measured. For Einstein, the universe was an ordered whole, waiting to be fully understood. Between them lay the great tension of quantum mechanics, certainty versus probability, realism versus mystery. And perhaps both were right, in their own way. Quantum mechanics continues to succeed as a theory, and yet the question of what it means remains open. The cat is still in its box, the dice are still rolling, the moon is still shining, whether or not we look, or is it? When Einstein, Podolsky and Rosen wrote their famous paper in 1935, they intended to expose a flaw in quantum mechanics. They wanted to show that the theory was incomplete, that it left out some hidden layer of reality. The example they used, two particles linked across distance, seemed to them an absurdity. They called it spooky action at a distance, and they believed that no serious physicist could accept such a thing as real. But what Einstein dismissed as absurd, the quantum world seemed to embrace. That strange connection, that invisible thread between particles, became known as quantum entanglement. Entanglement begins when two particles are created in such a way that their properties are correlated. Imagine a pair of electrons born from the same event. By the laws of physics, if one spins upward, the other must spin downward. If one has one property, the other has the opposite. This correlation is not strange by itself. It's like two gloves in a box, one left and one right. Pull one out, and you instantly know the other. But in the quantum world, the story is far stranger. Before measurement, each electron does not have a definite spin. Each exists in a superposition, both up and down at once. It is only when one is measured that its state becomes definite. And at that exact instant, no matter how far away, the other electron's state also becomes definite, perfectly correlated. This happens whether the particles are a few millimeters apart or on opposite sides of the galaxy. Measure one here, and the other knows instantly. There is no signal, no messenger travelling between them. The connection is outside the limits of space and time as we understand them. Einstein hated this. To him, it violated the principle of locality, the idea that nothing can affect something else faster than light. If entanglement were real, then reality was not local, and the fabric of cause and effect was deeper and stranger than he could accept. For decades, the physics community largely set the question aside. Entanglement was treated as a philosophical oddity, a ghost in the mathematics. The calculations worked, the predictions matched experiment, and so most scientists chose the Copenhagen path: shut up and calculate. But in the 1960s, a physicist named John Bell revisited the problem. Bell realised that entanglement was not just philosophy, it could be tested. He derived what became known as Bell's theorem, showing that if hidden variables existed, certain limits would appear in the correlations between entangled particles. If those limits were violated, then no hidden variable theory could explain the results, and quantum entanglement would have to be real. The challenge was clear: perform the experiments. In the 1970s and 1980s, physicists did exactly that. The most famous experiments were conducted by Alain Aspect in France. He and his team created entangled photons and measured their polarizations at separate detectors. Again and again, the results violated Bell's limits. The correlations were stronger than any hidden variable theory could allow. Entanglement was real. Einstein's spooky action was not an illusion. It was a feature of the universe. This result shocked many. It meant that the quantum world was non-local, that particles could remain linked across space in a way that defied classical intuition. The universe, it seemed, was more connected than we had ever imagined. Entanglement did not remain a curiosity. It became one of the central pillars of modern physics, with profound implications. It is the basis of quantum cryptography, where information is shared in ways that cannot be intercepted without detection. It powers the emerging field of quantum computing, where entangled states allow calculations far beyond the reach of classical machines. It even shapes discussions about black holes and the fabric of space-time itself. But beyond the technology, entanglement carries a philosophical weight. It tells us that reality is not built from isolated parts, each with its own independent existence. Instead, it is a web of relationships, where the whole cannot be reduced to the sum of its pieces. Two particles, once entangled, are no longer two separate things. They are a single system, no matter how far apart. This challenges our deepest intuitions. We are used to thinking of the world as made of objects, stones, trees, planets, each with its own identity, each existing on its own. Entanglement tells us that, at the quantum level, this view is incomplete. Reality is less like a collection of objects and more like a vast interconnected tapestry. Even the language we use struggles. We speak of one particle influencing another, but that suggests a signal, a cause, a chain of events. Entanglement is not like that. It is not a message sent across space. It is a unity that was always there, revealed when we choose to look. To Einstein, this was unbearable. He could not accept a universe where distance and separation were illusions, where chance ruled, and where certainty dissolved into probabilities. For Bohr and the Copenhagen school, it was simply the way of things. Strange, unsettling, but true. And for us, nearly a century later, entanglement remains both a mystery and a resource. It is at once the strangest feature of the quantum world and the key to unlocking new technologies. It challenges not only physics but philosophy, forcing us to ask, what does it mean for two things to be connected? What does it mean for reality to be whole? Perhaps the most haunting part of entanglement is its simplicity. The setup is easy to describe. Two particles linked by a common origin measured far apart, and yet from that simplicity emerges a truth that bends space, time, and logic. Entanglement tells us that the universe is not made of separate pieces moving independently. It is a single, intertwined fabric, where what happens here can be bound to what happens there, instantly and irrevocably. It is Einstein's nightmare and quantum physics' triumph. For decades after its birth, quantum mechanics lived in the world of theory and laboratory puzzles. It explained the behaviour of atoms, molecules and light. But for many people it felt like an abstract science, distant from daily life. The thought experiments of Einstein, Bohr and Schrödinger seemed more like philosophy than engineering. And yet, quietly, quantum mechanics began to reshape the modern world. Its strange principles became the foundation of technologies that touch every part of our lives. The first great revolution was the transistor, invented in 1947. At its heart, the transistor is a tiny switch that controls the flow of electrons through materials. Without quantum mechanics, its design would have been impossible. Transistors became the building blocks of modern electronics, shrinking from bulky vacuum tubes into microscopic circuits. From them came computers, smartphones, satellites, and the entire digital age. Closely linked was the invention of the semiconductor, understanding how electrons move in crystals, how they form bands of allowed energy states, required quantum physics. This knowledge gave rise to microchips and the information revolution. Every time you send a text, stream a video, or make a call, you're using quantum mechanics. The second revolution came with the laser. The word itself stands for light amplification by stimulated emission of radiation, a principle that emerges directly from quantum theory. Atoms can be nudged into excited states, holding on to energy like a loaded spring. When they release that energy in the form of photons, the process can be amplified, producing beams of light that are perfectly synchronized. Lasers now guide surgeries, carry information through fibre optic cables, scan barcodes at supermarkets, and even enable the internet you're listening through. All of it comes from manipulating quantum states of matter and light. Another application was magnetic resonance imaging, or MRI. This medical technology, which peers inside the body without surgery, depends on the quantum spins of atomic nuclei. When placed in a magnetic field and nudged with radio waves, these spins reveal the structures of tissues, allowing doctors to diagnose illnesses with extraordinary precision. Quantum mechanics helps save lives every day. And yet, these were only the beginning. In recent decades, physicists have begun to dream even bigger, to harness the strangest features of the quantum world not just for explanation, but for entirely new kinds of technology. One of the most striking is quantum cryptography. Traditional encryption relies on complex mathematics, codes that are hard to break with ordinary computers. But quantum cryptography takes a different path. It uses the principle that measurement itself disturbs a quantum system. If two people share entangled particles to form a key, any attempt to intercept or measure those particles will change them, revealing the intrusion. In this way, quantum communication offers security guaranteed not by human cleverness, but by the laws of physics. Another frontier is quantum computing. Classical computers, no matter how powerful, operate on bits, tiny switches that can be either 0 or 1. Quantum computers use qubits, quantum systems that can exist in superpositions of 0 and 1 at the same time. Entanglement allows qubits to link, creating a computational power that grows exponentially with each added unit. Problems that would take classical computers billions of years could, in principle, be solved by quantum machines in hours. The promise is staggering. Quantum computers could revolutionize medicine by simulating molecules with perfect accuracy, designing drugs and materials impossible to calculate today. They could transform logistics, finance, and climate modelling. They could even crack the most complex codes, changing the landscape of cybersecurity forever. But building such machines is one of the hardest engineering challenges ever attempted. Quantum states are delicate, easily disturbed by their environment. Keeping qubits stable long enough to perform calculations, a challenge known as decoherence, is like balancing a spinning coin in a storm. Yet laboratories around the world, from universities to tech giants, are racing to make it happen. And though the technology is still young, progress is real. Quantum computers already exist in prototype form, solving small problems beyond the reach of classical systems. Another emerging field is quantum sensing. By exploiting the sensitivity of quantum states, scientists are building instruments of unprecedented precision. Quantum clocks, for example, measure time so accurately that they would lose less than a second over the entire age of the universe. Such clocks are vital for GPS systems, space exploration, and scientific research. Quantum sensors also promise breakthroughs in detecting gravitational waves, mapping the Earth's magnetic field, and even diagnosing diseases. Entanglement itself is becoming a tool. Networks of entangled particles could one day form the backbone of a quantum internet, a communication system with unbreakable security and unimaginable power. Just as the classical internet reshaped the late 20th century, a quantum internet could transform the 21st. It is remarkable to think that all of this comes from principles once dismissed as absurd. Einstein mocked entanglement as spooky action. Schrödinger invented his cat to highlight how strange the theory was. Yet those very strangenesses are now the basis of our most advanced technologies. What once seemed like philosophy has become engineering. Still, quantum technology carries more than promise. It also carries responsibility. A world with quantum computers and quantum networks will not simply be more efficient. It will be different, reshaped in ways we cannot fully predict. Old codes may become obsolete, old strategies useless, old limits erased. The future will not just use quantum mechanics, it will be defined by it. And so, as we move deeper into the quantum age, we return to the questions that haunted Bohr and Einstein. What does it mean for reality to exist as probabilities? What does it mean that observation shapes outcomes? What does it mean that particles can be connected across distance? In the laboratory, those questions become circuits, algorithms, and devices. But in the human mind, they remain mysteries, reminders that the universe is stranger than we imagine, and that we're only beginning to learn how to live within its strangeness. Quantum mechanics began as a puzzle about glowing metals and spectral lines. It grew into debates about dice and cats. Now it is becoming the engine of technology, reshaping medicine, communication, computation and exploration. The quantum future is not coming. It is already here. Quantum mechanics is the most successful scientific theory ever created. It predicts experiments with breathtaking precision. It explains the structure of atoms, the stability of matter, and the chemistry of life. It powers lasers, computers, and satellites. Yet, for all its triumphs, it is also filled with paradoxes, puzzles that defy intuition, contradictions that sit at the heart of its mathematics. These paradoxes are not signs that the theory is wrong. On the contrary, they are signs that it is right, and that our common sense is too limited to grasp it fully. Each paradox pulls at the threads of reality, showing us how thin the fabric of our understanding truly is. The collapse of the wave function. Perhaps the most basic paradox is the collapse of the wave function. Schrödinger's equation describes a smooth, flowing wave of probabilities, but when we measure, that wave seems to snap, collapsing into a single outcome. For example, in the double-slit experiment, an electron passes through both slits at once, existing as a wave. But the moment we measure which slit it went through, the wave disappears, and the electron behaves like a particle. What causes this collapse? Is it a physical process, some hidden mechanism in nature? Or is it simply a reflection of our knowledge, the moment when uncertainty becomes information? This paradox cuts to the heart of quantum mechanics. If the wave function is real, then collapse is a violent rewriting of reality every time we measure. If it is not real, then what is guiding the particles before we look? Schrödinger's cat. Schrödinger's famous thought experiment remains the most vivid illustration of this paradox. The cat, both alive and dead until observed, is absurd at the macroscopic level, yet it is only a straightforward extension of quantum principles. The paradox is not about cats. It is about the fact that the mathematics that governs electrons seems to apply to everything, including us. Are we too in superpositions until choices are made? Does the universe itself exist in a blur until measured? The delayed choice experiment. Another paradox comes from experiments inspired by physicist John Wheeler, known as the delayed choice experiment. Imagine running the double-slit experiment but deciding after the electron has passed the slits whether to observe its path. If you choose to measure which slit it went through, the interference disappears. If you choose not to, the interference returns. The strange part is that your choice seems to affect the past. The electron decides whether it went through one slit or both, depending on a measurement made after it has already passed. This raises haunting questions. Does the future affect the past, or does the electron carry both realities with it until observation fixes the story? The quantum Zeno effect. Another paradox is known as the quantum Zeno effect, named after the ancient philosopher Zeno, who described paradoxes of motion. In quantum mechanics, if you observe a system continuously, you can freeze its evolution. A particle that might decay, for example, will not decay if it is measured constantly. Observation itself alters not just outcomes, but the flow of time for the system. This defies the idea that measurement is neutral. In the quantum world, to watch something is to change it. The many worlds idea. One way to escape the paradox of collapse is the many worlds interpretation. Proposed by Hugh Everett in the 1950s, it suggests that the wave function never collapses. Instead, every possibility happens, but in different branches of the universe. In one branch, the electron goes through the left slit. In another, the right. In one branch, the cat lives. In another, it dies. We experience only one branch, but all branches are real. This solves the paradox of collapse, but at a staggering cost. It implies an ever-splitting multiverse, with countless versions of ourselves living out every possible outcome. It raises questions as strange as the ones it tries to answer. What does it mean for reality to exist in parallel, forever dividing? Quantum non-locality entanglement adds another paradox: non-locality. Two particles can be separated by vast distances, yet remain connected. Measuring one instantly determines the other. No signal passes between them, yet they act as one. This violates classical notions of locality, the idea that things here cannot be instantly affected by things there. The Paradox is that the universe seems to ignore this rule. It is not built from independent pieces but from inseparable wholes. Wigner's friend. Another famous puzzle is Wigner's friend, proposed by physicist Eugene Wigner. Imagine a scientist inside a lab measuring a quantum system. To her, the wave function collapses when she observes the outcome. But to someone outside the lab, who has not yet looked, the entire lab, scientist included, is still in a superposition. This paradox asks, does collapse depend on who is observing? Is reality relative, depending on the observer's point of view? Or does it require consciousness itself? Why paradoxes matter? These paradoxes are not simply mind games. They reveal the strangeness at the core of the quantum world. They force us to confront the possibility that reality is not as solid, objective, and independent as we thought. Some physicists, following Bohr, accept the paradoxes as part of the deal. Quantum mechanics, they say, is not about describing what is, but about predicting outcomes. The paradoxes dissolve if we stop asking forbidden questions. Others believe the paradoxes point to a deeper theory still waiting to be discovered. Perhaps there are hidden variables, or new physics beyond quantum mechanics, that will restore order. And still others, like Everett with many worlds, embrace the strangeness, proposing that reality itself is vast and layered beyond imagination. Living with paradox. For us, the paradoxes are both unsettling and inspiring. They show us that the universe is not limited by human intuition. They remind us that the categories we cling to, past and future, here and there, alive and dead, may not be ultimate truths. Instead, reality may be a dance of possibilities, a web of connections, a branching tree of worlds. It may be that paradox is not a flaw but a clue, pointing us toward a deeper understanding. Quantum mechanics, for all its successes, leaves us with riddles at its heart. And perhaps that is the greatest paradox of all, that a theory so precise, so powerful, so indispensable, can also be so mysterious. It works better than any theory in history. Yet no one fully understands what it means. And so we live with the paradoxes, as physicists, as philosophers, and as human beings. We live with cats that are both alive and dead, particles that are both here and there, futures that shape the past, and universes that multiply without end. Quantum mechanics does not just describe the world. It challenges our very idea of what a world is. By the middle of the 20th century, physics had achieved two breathtaking successes. On one side was quantum mechanics, explaining the invisible world of atoms, electrons, and photons. On the other was Einstein's relativity, explaining the vast world of planets, stars, and galaxies. Each theory was a masterpiece, tested and confirmed with stunning precision. Each had transformed human understanding. But there was a problem. The two did not fit together. Relativity described space and time as a smooth fabric, warped by mass and energy. It dealt in geometry and continuity. Quantum mechanics described particles and fields as discrete, probabilistic and fuzzy. It dealt in jumps, uncertainty and probability waves. Together they painted two very different pictures of reality. And yet, the universe is one. The cosmos does not separate itself into quantum and relativistic domains. Atoms exist inside stars, and black holes crush matter to quantum scales. If our theories are to describe reality, they must somehow be joined. This search for unity has driven physics for nearly a century. Quantum meets relativity. At first, progress was hopeful. Einstein's special relativity merged with quantum mechanics to produce a framework known as quantum field theory. Here, particles were described not as independent objects, but as excitations of underlying fields that filled space. Electrons were ripples in the electron field, photons in the electromagnetic field. This new theory not only fit relativity, it explained phenomena with unprecedented accuracy. The theory of quantum electrodynamics, refined in the 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, became the most precise theory ever tested. Predictions about the behaviour of electrons matched experiments to many decimal places. It was a triumph, and it won its creators the Nobel Prize. From there, the framework expanded. Quantum field theories of the weak and strong nuclear forces were developed, and in the 1970s they were unified into what became known as the Standard Model of Particle Physics. This model described a zoo of particles, quarks, leptons, bosons, and the forces that governed them. It predicted new particles, like the Higgs boson, that were later discovered. At small scales, the Standard Model worked. At large scales, Einstein's general relativity reigned. For most of science, the division was manageable. If you were building a laser, you used quantum mechanics. If you were calculating the orbit of Mercury, you used relativity. But at the extremes, the division became intolerable. Where theories collide. In the heart of a black hole, matter is compressed to unimaginable densities, and gravity is so intense that quantum effects must matter. Near the beginning of the universe, during the Big Bang, the cosmos was a seething quantum soup under extreme gravity. In these places, neither relativity nor quantum mechanics alone is enough. Both must apply, and yet, when combined, they produce contradictions. Try to quantize gravity the way we quantize electromagnetism, and the math explodes with infinities. Try to describe space-time as smooth while allowing quantum fuzziness, and the very notion of smoothness dissolves. Physicists found themselves with two perfect theories that refused to speak the same language. It was as if one described the grammar of particles, the other the poetry of space-time, and no translator could be found. Attempts at unification. Over the decades, many attempts have been made to bridge the divide. One approach is string theory, which suggests that the fundamental building blocks of reality are not point-like particles, but tiny vibrating strings. Different vibrations of the string correspond to different particles. In string theory, gravity arises naturally as one of the string's modes. It offers a way to unify all forces and particles in a single framework. But string theory requires extra dimensions beyond the familiar three of space and one of time. It is mathematically elegant, but so far it lacks experimental confirmation. Critics call it beautiful but speculative, a theory in search of evidence. Another approach is loop quantum gravity, which attempts to quantize space-time itself. Instead of being smooth, space and time would be woven from discrete loops, like a fabric made of tiny threads. This theory preserves many features of general relativity while bringing in quantum principles, but it too remains incomplete. Others explore ideas like emergent space-time, where space and time themselves arise from more fundamental quantum structures, or holographic principles, where the universe is described as information projected from a deeper reality. Why it matters. The search for unity is not just academic. It cuts to the heart of our understanding of reality. Without a theory that unifies quantum mechanics and relativity, we cannot fully describe black holes, the Big Bang, or the ultimate fate of the universe. We cannot know whether space-time is truly continuous, whether the singularities at the heart of black holes are real or illusions, whether time itself is fundamental or emergent. It is also practical. Technologies born from quantum mechanics and relativity already shape our world. GPS relies on relativity, semiconductors on quantum mechanics. A unified theory could unlock new realms of technology, perhaps even new forms of energy or entirely new physics. Einstein's dream for Einstein, the search for unity, was personal. After completing general relativity, he spent the rest of his life chasing a unified field theory that would connect gravity with electromagnetism. He never accepted quantum mechanics as final, believing there must be a deeper order beneath the probabilities. Though he did not succeed, his dream of unity inspired generations. Today, physicists continue that quest, armed with tools Einstein never had: particle colliders, space telescopes, and the mathematics of string theory and beyond. The mystery of unity. And yet, the mystery endures. Perhaps unity will come from a single elegant equation, as it did for Newton and Maxwell and Schrödinger. Or perhaps the ultimate theory will be stranger than we can imagine, beyond the limits of human intuition. What is certain is that the search for unity is also a search for meaning. It asks whether the universe is ultimately whether its forces and particles and space-time are facets of a single reality. Quantum mechanics taught us that reality is uncertain, probabilistic, strange. Relativity taught us that space-time bends and flows, that time itself is relative. To unify them would be to glimpse the deepest structure of existence, and so physicists press on, through paradox and speculation, through mathematics and experiment, seeking the thread that ties the small to the large, the quantum to the cosmic. Perhaps one day the fabric will be revealed. Until then, the search for unity remains one of humanity's greatest adventures, a reminder that even as we master technologies born from these theories, the universe still holds secrets we have yet to uncover. Quantum mechanics was born from humble puzzles, the glow of heated metals, the emission of light from atoms, the strange behaviour of electrons. From those puzzles came a revolution, reshaping science, philosophy and technology. Now, more than a century later, quantum mechanics is not only the most accurate scientific theory ever devised, but also one of the most mysterious. It works flawlessly, and yet no one fully understands what it means. So where does quantum physics go from here? What is its future? Expanding technology. One clear path is technological. Already, quantum mechanics has given us transistors, lasers, MRI scanners, and the digital age. But the next wave of quantum technology promises to be even more transformative. Quantum computing is perhaps the most famous frontier. By harnessing superposition and entanglement, quantum computers could solve problems classical machines never could. They may revolutionize cryptography, chemistry, medicine, and artificial intelligence. Though prototypes are fragile and limited, progress is accelerating. What once seemed science fiction may, within decades, become a new layer of civilization. Alongside computing is the idea of a quantum internet. Using entanglement, scientists envision networks that transmit information with absolute security, immune to eavesdropping. Such a network would connect not just computers, but laboratories and satellites, enabling collaboration on a global scale. Quantum sensors are another frontier. By exploiting quantum states, scientists are building instruments of unprecedented sensitivity. These could detect gravitational waves more finely than ever, map underground structures without digging, or even monitor the activity of the human brain with extraordinary precision. In these ways, the quantum future is practical and near at hand. The mysteries of probability and superposition are becoming the engines of innovation. Deeper questions. But beyond technology lies something even more profound: the future of understanding. Quantum mechanics explains experiments flawlessly, but its interpretation remains unsettled. Does the wave function represent reality itself, or only our knowledge of it? Does collapse happen when we measure, or is every possibility real in branching universes? Does entanglement suggest that space-time is not fundamental, but emergent from deeper principles of information? Physicists debate these questions fiercely, and no consensus has emerged. The future of quantum physics will not only be about building faster computers, but also about wrestling with these philosophical riddles. One possibility is that a new theory will emerge, a framework that contains quantum mechanics as an approximation but goes deeper. Just as relativity expanded Newton's laws without discarding them, the next theory might expand quantum mechanics into something more complete. Some call this the search for a theory of everything, a unification of quantum physics with general relativity, a single description of the cosmos from the smallest particle to the largest galaxy, quantum gravity and the cosmos. The greatest challenge here is gravity. Quantum mechanics and relativity remain uneasy companions. Black holes, the Big Bang, and the fabric of space-time itself cannot be fully described without uniting the two. Some believe string theory will provide the answer, weaving particles, forces and space-time into vibrating strings in higher dimensions. Others look to loop quantum gravity, which suggests that space and time themselves are made of discrete loops, like threads in a cosmic fabric. Still others propose holographic principles, where reality is like a projection of deeper information. The future may reveal which, if any, of these paths is correct. New observations of black holes, gravitational waves, or the cosmic microwave background may provide clues. The quantum universe is not only small, it is written across the stars. Quantum and consciousness. Another frontier, more speculative but deeply human, is the question of consciousness. Some wonder whether the act of observation in quantum mechanics has anything to do with the nature of mind. Does consciousness collapse the wave function? Or is consciousness itself a quantum phenomenon? Most physicists are cautious here. There is no evidence that the brain is a quantum computer or that consciousness alters physics, and yet the parallels are tempting. Both involve mysteries of information, observation, and reality. In the future, neuroscience and quantum theory may cross paths in ways we cannot yet predict. Living with mystery. Perhaps the most important part of the quantum future is learning to live with mystery. For more than a century, quantum mechanics has challenged our deepest intuitions. It has shown us that particles can be waves, that cats can be alive and dead, that distant objects can remain entangled. It has forced us to accept probability, uncertainty, and paradox. The future may not resolve all these mysteries, it may deepen them. And perhaps that is the true destiny of quantum physics. Not to give us final answers, but to expand our imagination, to show us that reality is larger than our common sense. This human story. In the end, the story of quantum mechanics is not only about particles and equations, it is about people. Planck, reluctantly proposing quanta, Einstein, daring to suggest photons, Bohr, insisting that measurement shapes reality, Schrödinger, dreaming of waves and cats, Heisenberg, embracing uncertainty, and countless others, from the past to the present, building upon their insights. The future will be written by new voices, new thinkers, new dreamers. They will stand on the same ground of paradox and possibility, and they will push it forward, just as the pioneers did a century ago. Looking ahead, as we look to the future of quantum physics, one thing is clear: it is not finished. The theory that began with a falling apple's cousin, the glow of a heated stove, now stretches across galaxies and into the smallest fragments of matter. And yet it remains a work in progress, a doorway into realities we have only begun to glimpse. Will we one day have a final theory, a complete understanding of quantum mechanics? Or will each answer open new questions, new mysteries, new paradoxes? No one knows. But perhaps that is the beauty of it. Quantum mechanics does not simply describe the universe, it teaches us humility. It shows us that the cosmos is richer, stranger, and more intricate than we can imagine. It invites us to explore, to question, to dream. And so the future of quantum physics is not just a story of science, it is a story of wonder.